All right, the general power rule for integration. One of the most common used substitution involves quantities in the integrand that are raised to a power. Because of the importance of this type of substitution, it's given a special name, the general power rule for integration. And basically, it's the same as the power rule for integration. You just have, if you have the form function to a power times the derivative of the function that was raised to a power, you can just add 1 to the exponent and divide by the new exponent, add your plus c. Okay, as long as the exponent is not equal to -1, because when you add 1 to that, you would get g to the 0 divided by 0, which is indeterminate. So if I look at this one, I have 3 times 3x minus 1 to the 4th. So that has the form u to the 4th times du. So I can just go straight to the answer. It would be u to the 5th over 5. So 3x minus 1 to the 5th over 5 plus c. Because it fits the rule exactly, you can just apply the rule exactly. You don't have to make any adjustments. So here I have 2x plus 1 times x squared plus x. Notice that this right here is the derivative of this factor. Okay? So here's the interesting thing. This factor is not raised to a power. Now, previously when we first started integrals, we said you can't antidifferentiate a product. You have to distribute it out or FOIL it out. And you could do that one this way, this one that way. But if you think of this as a quantity to the first power times the derivative of that quantity, then you can apply the general power rule and just get 1/2 u squared, or x squared plus x quantity squared over 2 plus c. All right, how about this one? Well, if you look at this, it almost fits the pattern exactly. The u prime, or the g prime rather, would be 3x squared, and I just have an x squared here. So if I make the substitution, multiply and divide by 3, okay, I would get my u to the 1/2 times the derivative of u, and then I have to have the 3 outside, the 1/3 outside. So then I can just make the substitution using the general power rule. So add 1 to the exponent, divide by the new exponent, and don't forget to have your 1/3 factor out front. So you get 2/9 quantity x cubed minus 2 to the 3/2 power plus c. All right, one more. Now this one looks pretty complicated, but you can't have division, so bring this whole quantity up, raise it to the -2 power. The derivative of the inside, so you have a quantity to the -2 power, the derivative of the inside would be -4x, but you just have x. So since I'm missing a factor of -4, I can multiply by -4 with the x and multiply by -1/4 as a factor outside, because the -1/4 and the -4 rather would cancel each other out. But I rewrite them to get the form. So then I just apply the power rule. Add 1 to the exponent, divide by the new exponent. Then when you simplify that, so this negative and this negative cancel. Since I have a negative exponent, I want to rewrite it as a positive exponent, drop it to the denominator, and it goes next to the 4 because the 4 is kind of already in the denominator. And since everything else canceled out, the numerator is just 1. So sometimes integrals involve quantities raised to power cannot be found by the general power rule. So if you look at these two integrals, this one, the substitution works well in the first integral, but not the second integral. And the second integral fails, the substitution fails because the integrand lacks a factor of x and you can't adjust for a factor of a variable. In this one, it's missing the 2 from the 2x, but I can just multiply and divide by 2 to adjust for the factor of the missing constant. This one can't multiply or divide to adjust for a missing factor of a variable. Fortunately, for this particular integral, you can expand the integrand of x squared plus 1 quantity squared. You can just multiply x squared plus 1 times itself, FOIL it out, get x to the 4th plus 2x squared plus 1, and then integrate that just normally as we normally would. All right, so I hope that was helpful to you.